Okay, now I should be able, okay, that was it. I'm glad I spotted that. Yeah, so sorry, 1E, it wasn't you, it was me, but I figured it out. So the need for MPLS is motivated by an interesting dilemma. So you guys remember we can all use private addresses. So on campus, if we were to look at our IP addresses at any given point, when you're on like the U of H campus, you'll find, as in most organizations, you have a 10 dot address. In my case, I've got a 172. If you look that up, you would find that's private also. So what this means is that no packet can ever exist on the internet with this IP address in it. If a router sees it, it'll drop it. So why do we do that? We do that so we can reuse this block of addresses a million times over. So if 1,000 organizations decide to adopt this range of IP addresses, it doesn't take anything out of the global remaining dwindling supply of public IP addresses because we can use them. But you can't really send a packet to the internet. And that's, of course, what all of us want to do. So that's why we have network address translation. That's why NAT exists. So we can have a big pool of addresses on campus and a very small pool of real, public, bona fide, genuine addresses. And every packet we send gets changed to one of those public ones for the duration of the connection. So if it's UDP, it's for one packet, and then it's gone. And it's there for somebody else to use. For TCP, you get to hold on to it for a little longer, but not for a giant long time. So it's a way of sharing. Just think about it as you go downtown for a big festival, there's a rack of 8 bicycles you can rent. You've seen this, right? Is that enough bicycles for all of us? Well, how about usually? Is it enough? Yeah, in practice, usually. Are the roads built big enough to handle all the cars at once? No, but it's usually good enough. So it's just number conservation. It's the same thing the telephone network does every time a restricted resource does. So we had to have sort of draconian number conservation methods. So let's say you're the phone company and you want people to buy some of these upgraded services from you. Maybe you offer them storage and backup. Maybe you offer them links to other cities. You can connect them to Amazon, web services, whatever they might want. So you've got a variety of users out here all using the same range of IP addresses. And here you are in the middle. And one of the places you can get people to is the real internet, capital I internet. So these people are usually going to use these things maybe to get a connection to a branch office. Maybe they have a little string of data they want to get to a customer. Maybe they do buy a connection from you that gets up to the internet as well. And they do all of this over a single physical cable here between their main building and the telephone company cloud. Maybe it's 100 meg internet. And so think about U of H. We have some traffic that goes to the University of Houston downtown. That does not need to go over the internet. It would be subject to being dropped. It would be subject to being eavesdropped. So if the phone company says, I can provide you a secure private connection there, it does not touch the internet. Okay, great. And then Victoria, and then UH Clear Lake, and we're building in a couple of more. And of course, there's maybe some administrators' offices, some suppliers, some research labs. So we actually have a decent size network. Not everything is sitting here. And all that doesn't need to go over the internet. And on the flip side, we do want people to get to the internet, but we'd like to monitor a little bit what they're doing. We got ourselves in trouble with Yahoo, as everybody has seen plastered all over our homepage, because enough people out on the internet marked emails coming from our addresses as spam to Yahoo that Yahoo cut us off. They stopped forwarding our emails for us. And so professors were complaining that the emails were the virus on your system. So things can get out of control. So for reasons like that, U of H also might want all the internet traffic from all of these locations, all these campuses, to come through one place here where it gets run through a firewall. Maybe packets get recorded. They filter out known malicious stuff. They look for viruses. They do deep packet inspection, and then they send it out to the internet. And stuff that comes in from the internet, they do the same thing to make sure it's as harmless as possible before they let it through. So there's a market. Someone needs to sell us this type of thing that'll let us aggregate all of our traffic around one campus. Think about a company like Xerox with 1,000 locations, or Cisco with 1,000 locations. Anybody know how many of the major 10 oil companies with franchise gas stations, how many of them there are? It's about 1 million of the ones based in Houston. So there's like tons of these things out there. So you can sell people these, and what protocol are they going to use? MPLS is kind of a layer 3 protocol. And some of these sit at 2 and some of them sit at 3. But really, are you going to, anybody here run MPLS on their laptop? Last time you updated your MPLS software? What do we run? What do we run? It's the main topic of the class, right? We run TCP/IP. So how is that going to work on this? In fact, not only do we run TCP/IP, but we're using a private address. And what are the odds that none of these other companies out here who are also customers of the same phone company network aren't using private addresses as well? So you can't have private addresses on the internet. That's one rule. But you also can't have the same address as someone else, whether it's private or public. You can't have that. So now the phone company's got this issue. I've got all these customers that want to get on my network, but they're all using the same range of private addresses. How am I going to keep them apart from each other? So the way you do it is by not routing based on IP addresses. You take their whole packet, you hide it inside of something else, and you get it organized with some other scheme besides IP. Because the IP addresses will conflict with each other and nothing will get routed. So there's a whole class of these technologies that you can use to do this. So it would be like if you wrote an envelope and you put box 6 as the address on the front. Is that specific enough? What if it gets a pile of envelopes in the mailroom, they all say box 6? Well, are they supposed to all go to the same place? Do they all, and somebody says, no, I have box 6. No, I have box 6. So you have to put those envelopes in something else and say, no, computer science department, box 6. No, this one's electrical engineering, box 6. No, this one meant math department, box 6. And so you hide this thing inside of something else. It's that kind of idea. So that's what MPLS does, is it takes these packets, and so we'll take a little bit about how it does it. So here's my normal IP header with my source and destination address and packet type and type of service field and header length and length of the entire packet, etc. And then I've got all the rest of my data in here, like my IP header. But here's what I've added. I've added this red thing in the middle. So I've modified my Ethernet frame. Again, we saw that we modified it once before for VLANs. Ethernet, one of the reasons why it's still around and it still lasts is because they let it get modified. It's flexible. Nobody has this religion. So the religious layer lost out. It's like Ethernet. It's got to be one way. You've got to read it from the scripture of how Ethernet was first invented. Thou shalt have this many bits in the header. Well, they've let it be more flexible. Right? So this is why we're still able to use it, because people like it. The addressing works well. But they stuck this stuff in the middle, and in this header you have what's called a label, and then you have some things that we've seen like time to live before. So what this label basically does is takes the place of an IP address. So when you have University of Houston downtown, and you've got a bunch of users here, and you have University of Houston here, the central campus, and you have a bunch of users here, and we're using 10.3 addresses there, and all of us on campus are using 10.2 addresses here. We don't conflict with each other. Charles Chambers, our network manager, made sure of that. But Rice sitting over here, they might use 10.2 as well. Charles might have shown them his plan, and they said, that looks pretty good. Let's do something like that here. So these things can't exist with each other. So as soon as you ship a packet out the back of your router, an MPLS switch, which is basically software running in a router, is going to take this over, and it's going to take your IP datagram, and it's going to hide it inside an MPLS frame, and it'll put a new number in here. And this number will tell you, does it go over this physical circuit? Does it go over this physical circuit? Does it go someplace else? So it's a complete parallel universe, and it works fantastically well. This is a huge market. So this is the way most companies ship their traffic around the world, is they use a label switching technology like this. They do not use the internet. So you can have a couple of examples now to refer to. One of them was the content distribution network, the people like Netflix that have their own private network. They can run whatever they want on it. They're the only ones on it. So they can run IP if they like, but they're not having to share it with anyone else. So they can manage the congestion and all of that. And then they plug into the internet in every city at a local ISP. And so that's one type of network that doesn't really run over the internet. And this is the other one. This is what most of the rest of the world has. So if AT&T, if that's who your internet provider is, needs to ship your traffic to a website that also happens to be on AT&T's network, that they're a customer as well, and it's invalid, they will not ship it over the internet. They'll ship it over their own network to get it there. And they'll use a technology like MPLS to get it there. Right? So if you decide you want a connection to ConocoPhillips because you have a research grant that they gave money to the university for you to study transaction speeds of credit card processing at gas station pumps, and there's a different protocol. They're trying to switch it to TCP to lower the cost because TCP, then maybe you want to link to them. So you can share documents. They don't want to use Dropbox. Maybe they feel like it's too insecure. So are you going to have to order a new circuit and have somebody dig a cable from here to there? No. Chances are both organizations already belong to the large label switched network available in your city. Most people are. And all it takes is a little software control to program a virtual circuit over that connection. So as long as they're willing to let you use some of their big pipe, that they have 1,000 virtual circuits going to all their locations around the world, plus some to the internet, etc., then you can just be one more that's added in there. You don't have to do this when you're on the internet. You don't have to tell someone ahead of time, this afternoon I'm going to want to send a packet to a web server that has a webcam in Russia pointed at the stadium for World Cup. So what do I need to do to get prepared for that? Nothing. You just send the packet, and the router will get it there. But for this type of technology, it's more secure. So if you plan to send data, they have to give you permission ahead of time. So we're back to kind of having to set it up a little bit, but it's all MPLS. There's other ones, frame relay is another technology. ATM was an older one that used to be real popular, asynchronous transfer mode. And they all basically accomplish the same thing, getting packets from one place to the other, but for these, you hide IP inside. And then it pops out at the other end, and no one had any idea what was going on in the middle. So chances are a lot of the packets that you send are going over this type of network, and you would never see it. You will never see a router, even though there are routers, because they're not running IP over the internet. So if you run a trace route, you will never see them. You can't ping them. If you run MPLS, and you've got some technology to do that, yeah, maybe if you're an administrator, you can. So there's a whole bunch of reasons. Security is one of them, but this is a very dominant technology. So if you go into a business and you're going to be buying networking from them, if you're super cheap, you can use the internet. But chances are you'll want to use something more like this. A big exception would be when you go home at night. If anybody here used a VPN before? Right, so usually use a VPN over the internet to build a tunnel back to an office location. So anybody use it to get to work? So or just to get to like Onion and Tor and places where you can like watch shows like all my Mexican students do. They taught me how to, oh, that's no problem. You want to watch a US show? No, just VPN here to this site and then it'll look like you're in the United States. So I could watch my DirecTV again. I could watch the Astros from Monterey. I'm like, how can you not watch the Astros? Yeah. It depends. It depends. Sometimes you do need to pay for a VPN. It all depends on if they charge you or not. I have a commercial one that I pay for. When I worked at Cisco, I had one that they gave me. But here's what they do. They hide your packets that are leaving your computer. They put them inside of something else so that nobody can see really what you're doing. They usually encrypt it as well. When it gets to the other end, there's a device that undoes it, and your packets just magically appear inside this remote organization. And to them, to everybody else, it looks exactly like you are there. They can't tell that you're really at home running a VPN because your packets were tunneled. Nobody can see a router. They can't ping it or trace route. They may see that you're slow, that your packets take a long time to get there. That may be a hint, but otherwise you look like you're at work. And because you look like you're at work, you have an IP address from work. When you set up a VPN, you DHCP for a new IP address, and it is given to you by a router at work. You are given a subnet mask by work, a domain name at work. When you look around for printers, you see the printers on the LAN at work. You don't see the one in your own house anymore. It's disappeared. If you use a backup service there, you don't see it. If you're using Dropbox, all your packets from Dropbox now go to work and then down the VPN tunnel to you. If you send an email to someone, it goes through the tunnel from work and out. So if you go to a site that work doesn't want to let you go to, then it's going to get blocked by work firewall. You are, in all intents and purposes, completely part of that office. That's what these networks do as well. Except they're usually done in the routers, so you don't have to run the software on everybody's computer one by one. Okay? So it also gives us the ability to do things that we've been dying to do, like since this router is running MPLS, it doesn't have to route the same way that the internet does. So I can send traffic different directions. You remember that was something we talked about the internet not being able to really do. And Cisco, the company that makes routers that most people use, their routers do all of this stuff. Everyone's routers do all of this stuff. So you don't have to lose anything you've learned about IP. You just also enable frame relay, or you also enable MPLS, or you also enable tunneling or something like that. Right? So this is one of the things that people want their routers to do. They also can do faster rerouting. There's a very different version of learning where other things are called linked state flooding, which is basically a way of learning where everybody else is quickly. Instead of having to wait all these rounds for everything to go, you can send out a message saying, everybody tell me who you are right now. Yes, I can take a drink. So it's like everybody at once. And so you'll build your table quickly. That's what you'll want to do inside of a business. You typically have more control over things. So here's what a forwarding table looks like. We've added an in label, where you're coming from. That's nothing we ever paid attention to before. We look at where you're going to. Okay, that's destination-based forwarding. That's the way IP works. And the interface that you go over, yeah, and then what's the destination that we're supposed to match you to. So we're now looking at these things called labels. They kind of take the place of IP addresses. So that's the net on MPLS. If you work for a large organization or you work for a carrier, you will become very expert at technologies like this. And you'll realize that you can get a lot of stuff done with them. One of the things you can do, for example, is watch the traffic as it arrives at this edge router at the edge of the University of Houston. And let's say you're running MPLS to AT&T, which is one of the connections they have. And you can do things with the traffic that you normally can't do on the internet. For example, you can look to see what destination port it's headed for. And if it's the one that Skype uses, you can put it in a queue that has less variability and delay and gets higher priority. Or if you see that it's coming from a port number that represents WebEx, which is running a WebEx client. I'm sending all kinds of traffic out of my computer right now. Some of it, a lot of it probably, is destined for WebEx, coming from a WebEx client. Only those packets you can prioritize. So you don't have to prioritize everything coming from my computer, but you can do those. Or you can do the opposite. You can deprioritize things and push them down if they're not important. So if it's just people doing backups, things like that, maybe you give those lower priority. Okay, makes sense? Cisco, where I worked, they would do something interesting at the end of the quarter, when it was time to run the financials. They used a software system called Oracle Financials to do it. And it took so much computing power that they would push other applications off. They wouldn't run lots of other things for people. And the same thing with WebEx. When WebEx starts to see a surge in load because we sell that service, and it runs in the same data centers as everything else the company has going on, we all get slowed down so that the customers can have the CPU cycles they need to run WebEx. So they don't have to buy a data center big enough just for WebEx. and then buy another data center for us, and then what are the odds that they're both going to be used perfectly all the time? No. You don't give each driver their own lane on the road. You pool. It's a lot more efficient. So the ability to manage this stuff is kind of interesting. Okay, so we're going to spend the rest of the time today going over what's been going on with data center networks. Basically, the fundamental point I want to make about this is when you start taking a bunch of computing that used to happen in thousands of locations around your organization on small PCs, a print server, a file server, on and on, and you pull all of that together and aggregate it much more efficiently into a smaller number of servers in the data center, that's great, fantastic, pat yourself on the back. But all the computing I/O, all the networking that also used to be spread all over, now is all also concentrated in one place. And it's a much bigger problem because it's a whole lot more data that you have to network that's sitting in one spot. So data centers broke networking. Most of the protocols that we've talked about won't work inside massive data centers. So think about the routing protocols we talked about. One data center calculated that despite the fact that it's a very controlled environment and nothing changes, so links aren't going down unexpectedly and people aren't digging up cables inside the data center, it's one of the most controlled environments you'll ever see. Despite that, the routing protocol still shares every 30 seconds or a minute its routing table with neighbors. And so they found they were using something crazy like 50% of the router CPU power, 30% of their overall networking capacity, just to send updates among these tens of thousands of routers in a data center where nothing changed. It was pointless. It's like you should stop doing it. So that's one example. Another one would be if you know you've got a really big connection from one side of the data center to the other, and you know exactly how big the connection is, why would you start TCP at a window size of 1 when you know that it's going to get to a window size of 4,000? Why not just start with 4,000? Why start at 1 and do and play that game? You know, it's a dedicated network. You have complete control over it. So people started hacking the way this stuff worked. And what it's led to is a complete second set of modified protocols and equipment that run in data centers that we don't use anywhere else. And there's going to be a third wave of the stuff that's going to happen at kind of the absolute opposite end of that. So here we are in the middle. For 45 years, we've been using the same protocols with some updates. We've had to change them because of the massive concentration of what's going on in data centers. And at the other end of the spectrum, we'll have to change them again because of the tiny compute ability of the Internet of Things, the billions of devices that are going to monitor all kinds of things. The TCP may be too much for those. They need lighter weight, smaller things that can run on batteries. And one of the big problems with networking gear is there's no power saving mode. So they use the same amount of electricity all the time. That's a problem in the networking industry. Okay, so what is a data center network? It's a concentration of data I/O that comes from concentrating all of your servers. So it's turned out to be a big issue. This is a 40-foot Microsoft container. A container is just like those metal containers you see pulled around all over Houston on the backs of trucks and on trains and that you see on ships. And there's some cool videos of where they tip over and like 1,000 Mercedes-Benzes go, falling to the bottom of the ocean. There's like stuff like that. It would be worth going to get them, I guess, but who wants to drive a piece of rust at that point? I mean, those companies, they just write them off. They didn't even go get them anymore. It's like they just start over. Like, really? You don't, but it's a Mercedes. You don't understand. So they're not waterproof. So you can put data centers inside of these things, and people do this all the time. You'll do it for a variety of reasons. One of the big ones is disaster recovery. If a tornado comes through and knocks your building over, it's going to take a while to rebuild it. So you can call Johnson Controls, the people that make the thermostats that none of us can ever really get into and change. They don't seem to really change anything in a room. That frustrated me for like 20 years. And they make these containers. And they will fit on the back of a truck and on a train. It turns out these containers, there's a huge worldwide infrastructure to manage these things. So there are helicopters that pick up these containers. So you can take these containers and put them anywhere. any place you like. So they'll show up with a bunch of containers and rebuild your data center in the parking lot for 3 or 4 months. You plug in cold water, network cable, and electricity, and that's it. Walk away. But increasingly, this container idea is used inside of regular data centers as well. And we'll talk a little bit about why. But the thing that's sort of antique about this picture is this image suggests that there's like this cool, Honda running on NOS type of look, with this blue neon, and there's an aisle that you can walk down. There's no lighting inside one of these containers. There's no space either. When Google builds one of these containers, they cram it full of 3,000 servers, and it shows up, and the cloud drops it in on one of their data center floors, and there's no way to get inside. It's just pre-built. That's the Lego part. And if a server fails, they disable its network port remotely and keep going. It's just a server. They've got a million more of it. When a third of them fail, or it's 3 years has gone by, cloud comes and picks it up and replaces it with another one. So if you never have to get inside of here, there's a lot of things you can do to save money. For example, instead of making the sides of your computer out of thick metal, you can make them out of aluminum foil. Maybe a little thicker, but one where if you ever try to take it out of the rack, it would fall apart. Because you just don't need to invest in thick metal that can stand removing it from the rack to work on it and putting it back in. You don't have to insulate the cables where they're flexible, power cord that I move 1,000 times. It can be such thin, inexpensive plastic that if you bend it twice, the cable will break because it's never going to get moved. So yeah, you might save a penny here and a penny there, but if you do this a million times, it adds up. So we see a whole class of equipment being manufactured predominantly by one company in China that none of us will ever see because it's only going to get used inside these massively scalable data centers. It's to the point where you'll build one of these systems for a particular program. So if there's a new multi-person game that's out and there are going to be 10 million users, you could build racks of equipment in a data center that have exactly the amount of RAM and storage and the exact amount of power supply and the CPU power that you need for that exact game. And you know it'll last for 3 years, and then you'll throw them out. You'll recycle everything. And how much of this chocolate should I make him eat? Thank you. You want some chocolate? Anybody? Why don't you take some and put it on some people's desks on your way back to it? Help me get rid of this chocolate. Yeah, good. Don't ask. Just give it. No, we're way past the nice phase. It's like, if I eat all that chocolate, I'm going to gain the weight I lost in Germany, and I don't want to. So AT&T has these things as well, as do carriers. They'll put switching centers, the telephone switching equipment. AT&T loses one of these buildings about once a year to fire or flood or earthquake or tornadoes, and they'll just replace it with that. The other time you'll use these things is if you're going to remodel. You need to tear yours down. It's not an accident. It's planned. You can use a temporary data center. So they make these things with offices in them. They make a cafeteria one. They make one with cubicles and all the ones with equipment and everything like that. You're the man. Thank you for this. Like I owe you big on this. So the way we build the networks traditionally is in this 3-tier. You're going to have to go get one of those pieces of chocolate, or he's not going to run out. Yeah, just grab him when he walks by, just jumping. We've got this tiering of switches. So you have a top of rack switch, and then there's redundancy across all of this stuff. Here they show a single border router, but we've already talked before. We usually have a pair of routers running standby, and one of them is connected to the other, and he's constantly going, "Are you there? Are you there? Are you there? Are you there? Are you there?" He's like you're like your pesky little brother that just wants, like, you just want to reach over and like, "Stop it!" And as soon as you stop answering, it takes over. So that's the way we build redundancy in that type of routing equipment. Okay, what else do I want to show you here? This is a picture from a while back of part of a data center. Can anybody make out what this is? Can you tell, like, what the view, where the view is from? So supposedly it's from above, and I've stared at this a long time, and I don't believe it. So the caption says that the book that came and said it was from above. I'm not buying it. I think it's just a normal side view because these really look like floor tiles to me. And these are racks, and here's a bunch of Ethernet switches at the top, and then there's some fiber running along here and a cable tray. This is a snapshot of a Google data center, what was inside one back in 2012. It doesn't look like this anymore. Now it looked a little different, and I'll fast forward and go backwards again here. That's what they look like now. So there's no air conditioning outside of these containers. You don't have to do very much. There's a data center in Allen, Texas. For some reason, there's a bunch of data centers in Allen, Texas, which is the northern suburb of Dallas. And one of them doesn't really have much air conditioning most of the time at all. They built computers. They refused to buy computers that needed refrigeration. And they only buy computers that can run on ambient temperature air. So it means you redesign the architecture of the board. You don't put all of your hot chips together. You have big radiators on tops of the chips. Have you guys ever looked at your motherboard and seen that metal-looking fan thing? That's a heat radiator. And so if you manage that correctly and you provide for enough airflow, like with a really tall ceiling, then you don't need to do it. And in fact, at this data center, they pull fresh air in from outside on days when it's cool, and they monitor it for poisons and for anthrax, and they have the ability to filter it if necessary. So it's highly secure, but they don't use electricity when they don't have to. A bunch of people have moved data centers to Colorado. Why? It's colder, right? You can use cold air most of the time. And it turns out this is a really big deal. We won't have time to get through all of this, but we'll try. One of the innovations they have is to let some aisles be hot aisles and some be cold. So instead of having the front of the equipment always face north, alternate the aisles. Just like at the grocery store. You have one aisle you face, behind it, it's facing the other way, so your cart can go down the middle. If you separated those two things of groceries and let the heat rise in the middle, because it all generated heat, that would be this concept. So you let cool air flow in and hot air goes up, getting rid of the forced air in the floor. We hired a contractor once. Oh God, it's like I'm having a flashback on this. It's like post-traumatic stress syndrome. We hired this contractor to come in and, under supervision of some knucklehead at the phone company, to air condition one of our central offices because we were starting to get a lot more computing power. It was turning into a data center, but we didn't know to call it that. And so we go to look at this thing, and they put air conditioning all over, like in the top, like you normally do, and it was all blowing air down onto the top of the racks. And we're like, hot air rises, you should put the cold air in the bottom. Like, what did you guys do? So they had to redo the whole thing. I think they spent like $250,000, and it was like a work of art, this tin and sheet metal, and so probably the union was really happy with it. So we learned a lot of stuff. For an optimized data center, you basically deal with the hot air someplace else. You get rid of as much of it as you can, just dump it out to the environment, God help the earth, and then you pull cool air in as you need over here. Right? So this is the way one of these things would work. Conventional architectures for power, why do we use direct current? First of all, were you guys aware that we use DC in data centers? We don't use alternating current. Do you know the difference? Does anybody know that anymore? DC, AC, a little bit, sort of. So AC is the wall outlet, 60 cycles a second, the polarity of the signal changes. DC, it's constant. So DC won't go very far, but it turns out to be much more efficient. So inside of a relatively small domain of a data center, 76% of the power you generate still is on the wire when you're done conditioning it, whereas it's only 40 to 68% with AC. You can get it up there. Of course, if you're Google, you're better than everyone else doing this, so you're at 80%, and you're probably higher than that. In fact, there's a couple of other diagrams in here that show something called PUE, power utilization efficiency. So if you take all the electricity you use in a data center, everything, the Coke machine, the lights in the parking lot, the badge reader, the space heater that you're not supposed to have under your desk, but I mean, they keep the thing too cold, and all that stuff, including all the computing equipment. And you divide it by the amount just the computing equipment needs, you come up with a ratio. of how much of your electricity is actually being used for computing. That's the purpose of the data center. So most data centers have a ratio of 3 or higher, which means that you use twice as much electricity to run all the non-computing stuff as you do to run the computing, which is horrible. We're really bad at this. Most data centers you walk into will be small like that. Google's the world's best and have been since the beginning. They basically need only 10% more power than what the computing uses to do everything else in the data center. Okay, so that's all we'll get through for now. We'll pick this up again. We're kind of at an important part in the chapter where we're going to do what's called a day in the life, where we walk through everything that happens from the time you turn your computer on to when you get a web page back from Google. Every protocol, every step, every packet along the way. Believe it or not, we're kind of there. So we're there kind of early. All right, guys. Thank you. Hope you did well on the exam. We'll grade them right away. Thank you very much for being